Okay, good morning everyone. So, welcome back to this class for reliability and failure physics of semiconductor device. So today we will continue for our introduction. So last week we have already briefly talked about what will be the major content in this class and what you will expect to learn. And then we also have been already shared some of the reliability issues or even some of the industry level reliability testing procedure, methodology, or even just like in this slide, the spec. If we try to qualify a certain technology, what actually the reliability testing we have need to perform. So I want to make some of additional comments. So last week we have already mentioned that ideally if we try to qualify for each technology, we have to perform the certain testing. Basically we follow the JDEC community. They define this spec. So we have the temperature cycling, H3 TRB, HTRB, HTGB, and so on and so on. And one thing we want to additionally mention is about the quantity here. So last time we have already mentioned that the quantity is 3 lots. So 3 lots is actually from the 3 different manufacturing lots. So we will select the 3 different manufacturing lots, and then the purpose is to ensure the broad sampling. This is to make sure that once we test the stability of our manufacturing product, we have to reflect a broad sampling of the manufacturing process. Rather than we just only test a single lot, but we would pick out the 3 different manufacturing lots. And then each lot we will test for 7075 devices. So that's for each lot. So that means we will randomly take the 3 manufacturing lot, and then each lot we will take a 7075 device. So that means total we will test for around 200 devices. And then if all these 200 devices have been shown the very good stability, that won't have any fails, and that we can consider this technology has been qualified for the reliability testing. But for sure that how do we define the values? That's another very interesting knowledge we have to learn. Sometimes the value is defined as a completely broken. Sometimes the value is only defined as a certain parameter shift. For example, the threshold voltage shift to 0.5 volt or on resistance shift to more than 10%. We can also consider that as a value. We will talk about how to define the value later. Okay, so last week we stopped at the TDDB. So that's one of the main topics. In this class, we will talk about the time-dependent dielectric breakdown. How do we test it, and how do we understand the phenomenon happen in the TDDB? So, furthermore, we will also talk about some of the related to the reliability issue in the back end of the line here. So, imagine that we have one transistor in the last time we always talk about we always use the MOSFET as an example. So if we have the MOSFET structure like this one, so this is our source drain as a substrate, and then we have the gate metal on top. But actually, our real device not only contains this gate source drain. Actually, our real manufacturing manufacturing device actually consider lots of the interconnection line and lots of the passivation to protect our device. So once we have this gate source drain formation, we actually will start to make the interconnection line to connect the signal to the outside, to the region that we want to measure, to the region that we were interested to connect each device. So that's actually something that we need to also understand the reliability. And also, in between of these connections, these are all the interconnection line. We actually will try to have the good isolation, so we will have the lots of the passivation in between. That's because we want to have the good signal isolation between this and this. But if we don't have the good passivation in between, then actually our gate and source signal actually will start to influence with each other. And afterwards, so we have the interconnect, and then in the region between the interconnect and also the source region or drain region, this is something that we call the contact. So it's basically the interface between the metal and then the semiconductor. As long as we have the different interface between the material, they must have some important physics for sure that that's also related to the contact region here. So in general, what we usually call in this part before when we consider the semiconductor manufacturing, we make the device up to the gate side, up to the gate dielectric. That's usually we consider this as a front end. But once we have the interconnection and passivation afterwards, then actually this is what we call the back end. This is what we call the back end here. So we are not only have to consider the front end reliability. Front end reliability is mainly related to what we have been mentioned, like the BTI. TDDB is also related to gate dielectric. That's related to front end reliability. But to be honest, we also have what we generally call the back end reliability. So basically, reliability is everywhere. As long as you have one semiconductor device, actually all the region, no matter for front end, back end, even for packaging, all possibly to induce reliability issues. And one of the recent challenge for the back end reliability is related to we try to scaling our pitch. So once we talk about scaling, most of us will only think about probably we just make our channel length this place as smaller as possible, dielectric as thinner as possible. Actually, we also have to scaling this contact region as well. So we can consider this region as A. So to make our transistor with a higher density in a certain area, so basically we have to scale everything. We have not only scale our channel length, not scale our dielectric thickness, but we also will scale our contact area, and also even with the interconnection line. So with a very basic high school physics that we already know, if our contact regions become smaller, but what actually the current needs to be flowed in this interconnection line is the same. So that means actually our current density will be increased, right? Because of the current density is equal to the current over the contact region. So if we fix with the current, we assume there will be a fixed amount of current need to flow in this interconnection line. But once we do the scaling of our contact area, and actually our current density will increase. And once the current density increase, actually we will start to induce the reliability issues. Which is related to what we call the EM. We will talk about later. That's we call the electron migration. And this is related to the mass transport induced failure. And why we call this mass transport induced failure is this is because imagine you just consider the a piece of the interconnection line here. So we have this is the piece of the interconnection line. And most of the time we use the copper as an example. So the copper interconnection line has been widely used in the semiconductor industry. So if we call the left-hand side is a positive bias, that we should call as an anode region. And the right-hand side, we call this as a cathode region here. And once we have the huge amount of the electron flowing in this interconnection line, we actually find out that there's a problem with this interconnection line. This is because we have the huge amount of the electrons will try to flow to the positive bias region, right? So because we give the positive bias here, so our electron will try to flow to the left-hand side. But the problem is that this copper here actually will also be influenced by this electron as well. So we have the copper atoms in the interconnection line. This electron movement will start to generate a loss of the momentum. So the momentum from this electron will start to transfer. So that means this electron will start to push this copper because of the momentum from this electron will start to transfer to these copper atoms. In the end, we will find out that the copper will also move. The copper will also move as well to the left-hand side, and that's what we consider layer is atom migration. Toward the anode side. So ideally, we have a one interconnection line, and then the copper is a fixed atoms inside this metal line. So ideally, there's no chance of this copper can be moved. But because of right now our current density is so high, so we have so huge of a amount of electrons start being flow inside this interconnection line. And once this carrier electron flow, actually the momentum will start to transfer and push the copper move toward to the left hand side, which is the anode region. And in general, we call this phenomenon as an electron migration. So then you can imagine that the one of the key reason is that because of electron movement has a huge, creates a lot of momentum transfer, and as long as we reduce the contact region, reduce the width of our interconnection line, actually our current density is getting higher. And once our current density is getting higher, and then you can expect the momentum will be higher as well. So momentum is higher, and that means that this phenomenon will getting more and more pronounced. So in general, the reliability issue, what we talk about in this class is generally become more serious and serious in the advanced semiconductor node, because of in the advanced semiconductor node we are expect the thinner dielectric, smaller pitch, thinner interconnection line, higher current density, or some of the application. We also even expect to the high frequency, higher power rating. So that's all will start to accelerate more about these reliability issues here. But you might curious about what happened to this copper movement here. But then we can use another example. Actually, in our semiconductor interconnection line in the back end, the interconnection line is not always just in the one direction. It's not always straight. You will find out that there is a very complicated connection for our interconnection line. Probably just like this one. So you will have the anode here, and then actually your interconnection line is not always designed as a straight. Sometimes you will design as like this one, because for some of the consideration, for example the layout consideration, to avoid the influence from the other signal or other transistor. So we will not always, or we can not possibly always design our interconnection line in the very straight line. It's always there's a certain deformation of our interconnection line. So imagine now you have the apply the voltage here. That's the anode region. So as we already know, we start to have the electrons movement inside this interconnection line. And also from the previous knowledge, we already know because of the momentum transfer, the copper atom will start to move as well. So then after a while, we will start to expect, or we will start to observe the copper atoms will start to accumulate in the third region. For example, like in this place. So we will have the copper will start to accumulate in this region. And in this case, with the time passed by, actually the interconnection line will become a kind of like the thicker. This is because they are getting more and more copper accumulation in the one region. And this is what we call the key lock. So we will have the key lock formation in the one region. but also because of the total amount of copper is fixed, it's the same. We actually didn't add more copper atoms in the interconnection line. So that means if there's a one side you have additional copper, that means there's another side, the copper will start to missing. Just like here. So the copper in this region will getting a decrease. So in the end, we will have the void formation. So after the certain timing, few hundred hours, 7,000 hours, we can start to see the Heat loss formation on the one region, and also we have the void formation on the one region. The problem is that if this void is start to growing as a bigger and bigger, that means the electrons can pass by this region is getting more difficult, and usually we will expect to see the open line here. So that means that some part of the interconnection line is completely broken. So that's in the end your interconnection line fail. So no matter how good the transistor front end you can make it, unfortunately, if the interconnection line there's a one open region, actually you cannot get the correct signal. On the other hand, this region also will create a problem because we are not here we only talk about one interconnection line, but in reality we have the 100 of the interconnection line. So that means there's always another interconnection line next to this one. There's always lots of a neighboring interconnection line. So this copper will start to get in touch with another interconnection line, and that will create the issue of the short. So anyhow, as long as we have the issue of the open or short, that always gives us a lot of the signal problem because we cannot correctly to get the right signal from transistor, from the transistor that we are interested in. So this slide is basically briefly explain that what happened related to the mass transport induced value. Why we call the mass transport? Because this movement of the one atoms in the copper in this case is we consider as a mass transport. In the end, this will create a value in here, like an open or short region. And this issue is getting more complicated as long as we have the scaling our interconnection line. And also this also getting the problem recently related to the 3D monosync integration chip, because in the 3D we also have the so many interconnection lines that need to be connected with each other. So that actually always create the issue of this electron migration. Okay, so the last one we will talk about here is about the electrostatic discharge. That's the ESD issue. This ESD issue is mainly related to the triple electrical charge. So what does mean the triple electrical charge? Is that you have two different material, and you suddenly with some condition, the charge from one material is possibly to move to another material, in the end to create the immediate like the electrical discharge, electrical shock here. So basically the triple electric charge is related to the ESD. So, triple electric. I think the triple electric things that you have been already experienced in the daily life, especially in the winter season or in the very dry region, you always been shocked if you try to touch some of the very specific material. For example, some metal, you will always, once you touch it, you will be in certainly like the shock. So that is what we call the triple electrical charge, 摩擦放电. So basically, we have the charge transfer between two materials due to contact separation. So this is a one schematic illustration. So actually there are lots of charge in your fingers. So once you touch your certain component, IC component, and you suddenly disconnect it, and actually there was a chance to generate this triple electric charge that's related to electrical discharge. And that's how we call this as a ESD event here. So ESD is also one of the key reliability challenges in the semiconductor industry, and we will also talk about ESD in this class. So this class, this is just try to overview what we have not discussed in this last week. So just want to share you that in the education field, many experts try to develop the different kind of the knowledge, try to understand that how people try to learn one thing or absorb one knowledge. And basically we can divide by 6 levels here. So you should always keep in mind is this 6 level, because that's good for your personal learning as well. So the basic level is always just to remember. And the second one is understand. And the third one is start to apply the knowledge you understand on the one thing, try to apply. And then the fourth one is analysis. So you start to analyze one thing based on what you have learned, what you have understood. And then once you start to analyze, you can do the evaluate. So you can start to figure out what will be the issues here. You analyze one particular reliability in the 2 different processes, and then afterwards you can evaluate which process that can be good for the reliability. And of course, once we have evaluate, the last and the most important is create. Since we understand which one is better, for example, you compare the 2 or 3 different design in terms of the certain reliability issue, and in the end you can figure out that which design is good to improve the reliability of your product. And last one for sure that you start to understand, and you can start to create. You can create a new product or new design based on what you have learned from the previous evaluation. So this 6 level of the different type of learning is pretty important. Of course, in the end, I think for everyone who is doing your thesis, your research, or even who is going to work in your future career, I think your boss, your manager expect you to have to create something that can be useful for the company. So for sure, the create is always very important things that you have to keep in mind. But of course, in this class, we probably will not be able to have the chance that you allow you to create something. But at least we hope we can reach to these 4 different levels. Is that in the end, by the end of this class, you are able to evaluate the reliability of the certain technology. You are able to analyze the reliability. You can apply some of the statistical tool or some of the equation to evaluate the reliability. Of course, the basic one is understand of all these reliability issues. And remember, I think it's not the basic part in this class, because we only have one open book exam in the end. So I don't expect everyone has to remember very clearly what's the equation, what actually the definition of each academic term. But so actually remember, it's not that important, but at least you have to understand. You have to understand like why this testing, this reliability is important, and what actually the value physics behind. Okay, so this course is designed based on what we call the constructive alignment. So constructive alignment is considered the 3 different pillars that in the end to create this class. So this constructive alignment is the way that the typical educational aspect, when they try to create the course content, they always try to fit these constructive alignments. So there's 3 different pillars for this one. And the first one is for sure, this also would be good once you study the new subject or doing something new learning for yourself. You have to first to figure out what will be the learning outcome. Thus we call this as an intended learning outcome. And based on this learning outcome, we will start to design several different teaching and learning activity. And of course, to help everyone to understand this class, we will have the assessment task. So these 3 will be well connected with each other. So that's why in this class, some part of the content has been already mentioned in the last week. Okay, so let's just a quick overview of what we have been discussed. So by the end of this class, you should be able to first to explain the basic operation principle and fabrication process for the MOS type semiconductor technology. Actually, we already start to explain to you the MOSFET, how actually the MOSFET operations. And also, second part, we will apply the basic statistical tool for reliability analysis. And that's pretty important because this is a pretty unique knowledge that you will only learn from this class, not ever from other classes. And the third one is you will start to evaluate the failure phases. So the one we are interested in this class is the BTI interface, TDDB, mass transport induced value, and ESD. And also, as we already discussed last time, you will be required to present reliability issues, use your own word, because that's once you can say something about that, that means you completely understand the knowledge here. And last one is we hope everyone can have a certain concept or mindset related to the design for reliability. What would be possible methodology or the design for the transistor design or fabrication and so on to improve the reliability for the device. I think we have already also mentioned that's related to teaching the TA. Okay. By the way, just one last reminder. So we will only upload the lecture note and YouTube in this Facebook and no more in the E3 anymore. So you have to log in this group to gather the latest information. This is we have already mentioned last time. Okay. Okay. So finally, we start to move to the real content related to the semiconductor. That's related to the past and then the future. So first of all, although I guess everyone here has already the basic understanding of semiconductor, but we still have to quickly overview the basic property for the semiconductor. So as you know, in the material world, we have basically the insulator that's based on, for example, glass or plastic, and we also have the conductor, for example, that's the metal. So the semiconductor is actually the material in between these two. So this is a material between the conductor and then the insulator. So as being an engineer, for sure, every time when we talk about, especially the electrical engineering, so I think for all of you guys, you come from different background, probably some from the material science, some from the physics. So the parameter you are interested in the past probably is not always related to current and voltage. But as long as you are in the electrical engineering field, what we care the most is definitely the current and the voltage. So therefore, we also will interested in that what would be the typical IV curve for the one semiconductor material. So the insulator means it's completely insulating. That means whatever the voltage you apply, you should have no current can be conducting in the insulator. So that's a basic definition for the insulator. On the other hand, the conductor means you apply the small voltage, but you can get pretty high current. So the semiconductor, in a very brief way to explain, it's just the material that exhibit the characteristic between the conductor and also the insulator. So that means we expect our semiconductor should have the characteristic just in between. That's a semiconductor. But the cool thing for semiconductor is not only in between, is we are able to a little bit adjust this conductivity. For example, we can try to fabricate the semiconductor toward the insulator. We can also fabricate the semiconductor toward the conductor, as long as for example, there are several different methodologies, as one most obvious and easy one is we just change the doping concentration. If you try to dope something, getting more and more, actually that will have the characteristic toward the conductor. If you try to dope with one concentration as smaller as possible, actually you can start to tune the semiconductor become the insulator. So that's actually one of the most powerful property for this semiconductor is we are able to adjust the conductivity by doing some additional process here. So a semiconductor material has an electrical conducting value. Falling between the conductor or insulator. So that's a pretty basic definition. Of course, this definition usually doesn't give us a lot of sense. So another very important property for semiconductor, as I already mentioned, we are able to adjust the conductivity by tuning the different doping concentration. So that's why the semiconductor material are very powerful for us. Of course, regarding to a semiconductor adoption trend, I think you guys also, we are very lucky in the age that the semiconductor technology is booming now. So we have so many electronics right now is all needs an advanced semiconductor device. So from the early time, from this is mainframe computing to the personal computing to the mobile computing, and nowadays every computing needs to be connected with each other. All are enabled by the semiconductor technologies. Of course, there's another trend is that with the last 10 years, because all these online stream, online software, search engine, and so on, and even the social media, that's create the explosion for this data traffic. And this data traffic or this data communication not rely on the some of the interconnection, like sometimes also rely on the wireless transportation. That's why we need to develop the very good semiconductor technology that actually help us to handle all these data that actually being generated every day, and then that need to be processed every day. So if you look back for what would be the 10 most important innovation in the semiconductor industry, I think the Dr. Morris Chang, his talk in the 2018, that's a 60 year. I think that's one of the forum to cheers for the 60 years of the semiconductor, and then I think he made a very great speech and summary that from his point of view, what would be the 10 most important innovation in our semiconductor history. So for sure, the first one is definitely related to the transistor. So the transistor will start to innovative. We start to propose, and then more and more innovators in this field started from the 1948, and afterwards. But the problem is that the first transistor is not made by the silicon, and then one of the reasons why semiconductor technology can be processed, can have the progress steadily, is because of we start to adapt the silicon material, because silicon material is easily accessed, and also is the cost is lower, so that's also is very stable material. So in the end, that start to help the semiconductor technology start to have the steady progress. And then 1958, we start to have the concept with the IC that we call the integrated circuit. So we are not only consider the single one transistor, we are actually trying to have the multiple transistors that are being connected with each other to produce some of the function that we want. And in the 1965, so we start have the Moore's law. So Moore's law is a law that predicts the density for the semiconductor generation, and then in the end it becomes the golden rule that the semiconductor company want to focus on. And then afterwards, I think the most important is related to the MOS technology, because you have to know in the beginning actually the silicon transistor actually is based on the bipolar junction transistor. It's not always based on the MOSFET. But since 1964, we start to have the MOS technology related, for example, the MOSFET. And also the silicon gate that's related to SiO2. And also the CMOS. These all three start to make the MOSFET as a main semiconductor technology, because of the silicon dioxide is a very stable dielectric in the MOSFET, and also it's very easy to process. And also we start to have the CMOS technology that we combine the PMOS and NMOS together. In the end, we are be able to realize certain of the logic function. And also afterwards, we have the memory technology. So especially related to the DRAM, and then the flash. And then you can see that probably some of the name you are familiar with is Professor Simon Sieb, and he is the inventor of the flash memory, and was the professor in the NYCU before, but he was passed away, I think, from the last year. Yes, because due to some of the cancers. And afterwards, people consider we cannot always fabricate and also do the assembly test in the one company. So we start to have outsource. We start to have the outsourcing of the assembling test. And then also in the 1970s, Intel start to have the microprocessor. And then afterwards, we start to have the VLSI system. So this also includes some of the IP and design tool, and because of the VLSI system, the fabless companies start to getting popular. because they can start to design their chips, and then, but once they design the chip, they need to have the dedicated place that can allow these chips being realized. That's why in the 1985, Dr. Morris Chang started to create a business model called the dedicated foundry. Because of this dedicated foundry, so that's why this is starting from 1985. And because of this dedicated foundry, that's why it's getting more easy for these families or design company to realize their goal. And also because of this dedicated foundry, that's why the TSMC start to bring another semiconductor, bring the semiconductor in another level of the business now. And I think this slide I have been using from 2018 so far. And it's interesting to know, if you back to several years ago, you probably use a different company as an example to illustrate why this IC design house needs this foundry. But in this year, also starting from last year, I think one of the most the iconic semiconductor foundry, a semiconductor company who really rely on the TSMC, and also he not only once, he continued to say again starting from 1990, and the first time he visited Taiwan is because of due to the business cooperation with TSMC. I think that's because that's just related to the NVIDIA. So NVIDIA, the one reason why NVIDIA can be succeed like nowadays is because of starting back to the more than 10 years ago. Already, they already start to work with the TSMC to realize their chip. And nowadays, they even consider the what they can achieve is mainly attributed to all the efforts come from the TSMC. Okay, so here is just some like the interesting picture. So that's a picture from 1958. That's the first IC, but this IC is based on the germanium. Of course, germanium has a problem which is related to not very stable. So that's why people will start to prefer use the silicon afterwards. And this is related to Moore's law. So basically, what Morse tells us is that the Moore's law is an observation that the number of the transistor in an integrated circuit double approximately every 2 years. So basically, the Moore's law is just an empirical model, but in the end, it found out that it can be realized, and then all of the company try to reach the Moore's law. So Moore's law in the end becomes the golden rule for the semiconductor company want to prove that they can achieve another level of their advanced technology development. Of course, there's some rumor recently say that the Moore's law probably is dead because of we cannot always make a transistor as smaller as we expect. But however, there's some other possibility try to keep the Moore's law. And then with this is one of the examples that the CMOS density is improvement, but we also will consider the high density SRAM, logic gate, and also transistor density. In order to reach this target to keep following of the Moore's law, actually there are already several important innovation that have already happened in the past. For example, the first one is a typical, that's we call the Danner scaling, like here. So that's related to we mainly scale the device with a one kind of like the factor here in this slide is related to the alpha. So that means that after certain generation, we will consider to scale the device just by the certain fixed ratio, scale our oxide by the fixed ratio, and also scale everything with only one fixed ratio. But of course, that's not enough. So that's why after the 2000, we start to expect some of the additional possibility with what we call the equilibrium scaling. So equilibrium scaling is mainly enabled by the high K metal gate. So the high K dielectric is include for example, like the hafnium oxide, like the aluminum oxide, and so on and so on. These are the high K materials. And the reason why the high K dielectric can help us to keep our current density still increase. This is because if we look at the typical curve for our MOSFET, it's what we consider as the IDVG. So our curve is roughly like in this way. And in later on, you should also be aware that the drain current is certainly proportional to our oxide capacitance. And the oxide capacitance is equal to our dielectric constant, X zone, over our oxide thickness here. So that means there's a two possible way if we try to improve our current. One possibility is we make our oxide thickness as a thinner. For sure, your current can be increased. But on the other hand, we cannot always try to reduce the oxide thickness as possible as we can, because they will be getting more serious of reliability issues that we will talk about later. So therefore, we think about can use another approach is if we can find a material that has a high dielectric constant. So if the dielectric constant is higher, then that's why the current can be increased as well. So now the conventional silicon dioxide has a dielectric constant 3.9. Therefore, if we can find a material that has a higher dielectric constant than silicon dioxide, then we can easily to increase our current. So for example, hafnium oxide has a dielectric constant around 25. So now you see, we don't do any like a scaling in the pitch. We don't do the channel scaling. We don't decrease the oxide thickness, but we actually just change the oxide material from the silicon dioxide to the high K material. Then we can easily to boost our current density. So that's the goal, because in the end, it's the Moore's law is related to how to increase the density. So as long as we can boost our current, that means we can also increase our density as well. And nowadays, we are also consider not only the technology optimization, but also related to design technology co-optimization. So for the design people, they should also understand what actually the advanced semiconductor look like. What's a FinFET, what's a CFET, what's a so on, what's a gallium nitride, and so on. And also for the technology people, also has to understand the basic related to the design and even for the circuit application. Because in the end, we have to consider this DTCO together to further improve the density of our transistor performance. Of course, again, if we purely only focus on the dimensional scaling, it's definitely under the pressure. So this is production now is in here. And then beyond, still in the R&D phase. And here is just one slide shows that how small the semiconductor device can be. You can see that right nowadays, the FinFET, advanced FinFET, the pitch for FinFET is already smaller than the virus. Of course, when we talk about the advanced transistor, it's always good first to understand a little bit about the evolution of microelectronics. So I think we will take a break for 10 minutes. We'll come back and we will continue to the introduction for some of the semiconductor technology from history to the future.我是帮你加进去了，这样子好。对对对，应该是加进去可以。OK。对对对，你那个系统上面应该是有的。对对对，那个是加进去。对对对，那应该就没问题。谢谢谢谢。
我记得是一开始有稍微讲一下怎么计算。
对。
然后那个 attendance 我也忘记，我不确定是我当时有听到还是就是我有看 attendance 有一个比例的分析，但那个是要怎么去进行？
就是没有，就是上课点名，就算我点名，对，
所以
就点名没到就没了。
对，所以我是会每次点。
看状况。对。我记得我把你加进去了。
我是这个对。
OK，因为这是OK。哎，我把你加进去了。
哎，对，
应该把你加进去了。
所以我应该还是要写的。
我不知道哎，我把你加进去，我觉得应
该是就不用，
应该是不用，但是如果你要画，
老师你看一下我写的。
对，好，不然先这道看吧。但是我觉得他如果申请了，可是那申请当什么数学？
对，然后我把它这个示范，在前面他说要改。OK， 但是他说如果不行的话，就问他为什么不行。
好，
我一直堵他。
对，
我一直堵他，堵到他看。
反正不行的话，我就打电话，因为有另外一个，所以我到时候再打电话去跟他问。
因为我看我们好像就是我们的 mail 的 CC 里面好像有好几个，好像也都是要改的，对不对？因为我看
应该没有，应该只有2个。
只有2个，
就只有2个。
OK， 好。
对，只有2个人。对，就跟那个陈威熙对。对。OK。
就是今天早上才寄信给你说。
没办法加，因为这个已经超过人数。对。
有人退掉或是。
可是有人退掉，基本上也是已经现在都已经超过了，现在都已经超6几个人。对，所以今天就没办法加进。对。
是啊。
可是我记得我已经把你加进去了。我觉得应该是不用了，但是我还是可以签一下。但是因为我已经把那个都直接加进去了。
如果是直接被加进去，就还要继续签吗？
我觉得应该是不用。对啊，因为你们在选择系统上面应该就已经看到。对。
我是那个 FB 社团，我上礼拜就申请了。
你叫什么名字？
我叫洪成，我刚刚有在申请。
等我一下。 洪承伟是不是 ？OK， 好，没问题。可是我应该加了，我是啊，真的吗？哎，那我看，那你给我比一下，
我进来一下。我看了。
你要比这个，我应该有蛮单的，对，
所以我不用再先加。
我觉得应该是不用了，但是我可以签一下。
然后呢，这就得要洗。
对。I think I already add you guys. I think I already add you guys in the system.
So you don't have to submit the document to the reference?
I can still sign the case.
I need to ask you because I have to reapply for the scholarship and I need to provide the reference from my advisor and I have to ask my teaching project because there is an option if they send you notification in your contact form or
You also try last time.
No, I didn't have to. I already did it the first time. I think I already did this during the application. If it's the same form.
Yes. Just try to make it a draft. Make it a draft.
Okay, so.
But usually I think they prefer to then just
Oh, okay.
yeah, let me select.
So you're fine with this?
Yeah.
Okay, then I do this.
Usually I just select.
Okay.
我知道。
就是那个我们这边有带那个加签单。
我觉得我要帮你加进去。
有啊，
对。
而且没有记清楚是不是你要签？
我觉得应该是不用啦。如果说你还是要签名的话，你再写信约时间。
哦。
对。反正我们现在我应该是把你直接加到信。
有，我有在系统。
对。
所以我在系统我就不用再。
我觉得应该是不用。我觉得应该是不用。
哦。
对。
现在是。
I think I already add you. By the way, can you give me your please use NYCU anymore. Please. Do not use NTHU.
Okay.
So can you also send me your NYCU?
Okay.
email?
Later.
Yeah. We won't use NTHU. And by the way, for the co-advisor sheet, you need to give to me. Yes.
The student.
Co-advisor sheet.
Okay.
You need to
Tomorrow.
give, yes, please give to me because I need to help to find the co-advisor.
Thank you.
那个要去找助教吗？
不用，你叫什么名字？
王松村。
OK， 好 ，OK， 好。 Okay, so let's look at some evolution of microelectronics from the early time till the most recent one. So from the beginning of the 90s, we mainly focus on the vacuum tube. And afterwards, the transistor will start to have, which are the bipolar and then the most important one right nowadays is a MOSFET. So actually, the bipolar transistor is still very important, but just used in the more specialty technology. But if you consider the logic application, the MOSFET now has become the dominating technology. And to further improve the performance for the MOSFET, actually we have several different strategies. And first of all, we have to understand the basic equation, the basic current equation for the MOSFET. So that's ID, the drain current in the saturation region, is proportional to the equation like in this: 1/2 mobility times Cx times our VGS minus VTH. So the equations look like in this way. So if you want to increase the drain current, that's one strategy is we need to increase the mobility. So that's why the first innovation in the MOSFET is trying to have the mobility improvement by new material. The idea is we want to have the higher on-state current. That's ID. That's ID. So there's several several innovations that we can try to increase the current. One is using the strength silicon, and one is using the germanium channel, and one is using the 3-5 channel. For sure, we will not talk about the detail for each one, because each one is nowadays way too complicated that you can spend like more than 5 years for the one specific technology. So in here, just give you some ideas that the first innovation that we will have is we try to have the new material that gives us a higher on-state current here. But the later on, we will start to suffer the issue is related to the short channel effect. This is because of as you know, this is a typical schematic for the MOSFET. We have a source and drain. We have the gate on top. And we have the gate metal here. And usually we call this as a channel length. As we call this as a channel length. And ideally, if the channel length is large enough, that's we call this as a long channel device. But if we have since the channel length here is very long, so the carrier, especially in this case, the electrons in the source, should always stay here. In the case without given bias, so there's no chance this carrier can be moved from left to right because this is a long channel device. But the problem is, if we start to make our transistor as a smaller again, this is a source and drain. This is a gate dielectric and this is gate metal. So if the channel length is smaller enough, that's we typically call this as a short channel. And we start to find out the electrons in the source side has a chance to tunnel to the drain side. And that's because of due to the quantum mechanics, that's due to a tunneling. So as the channel length is decreased, the carriers in the source side has a higher chance to be tunneled into the drain side. And if you look at again for the IV curve, especially the IDVG, but now we prefer to plug in the log scale. So in the long channel device, the device characteristic will look like in this way. So this is our threshold voltage. So because this is long channel device, so then the carrier here will be very difficult to be travel through to reach the drain side. So therefore we expect to have very low leakage current. That's a 10 to minus 12. But however, in the short channel device, here, actually the electron tunneling, this phenomenon is getting more obvious. So that means if you try to look at the short channel device, the IDVG is always starting from here, like this. And most important is this part is getting very high. This is a typical characteristic for the short channel, and this is for long channel. And usually we define this region, that's what we call the I off. And we can start to find out, once we reduce the channel length, actually our off current is increased, and therefore the on-off ratio is decreased. Right? Because right now in the past, this is 10 to minus 12. For example, if this is 10 to minus 1, so we have the 11 orders different. But now this is 10 to minus 6. This is probably like a 10 to 1, but we should only have the 10 to 7. We only have a 7 order different. So the on-off ratio is decreased. So that's become the new challenge if we want to make the short channel device. So Once we improve our current density, that's the first stage, but afterwards we found out that our off current is also increased. So the next innovation should be try to address this issue, try to reduce the off current, at the meantime to improve the on-off ratio. So there's several innovations in this way to address this issue. Actually, the improve the on-off ratio, sometimes we also call as electrostatic improvement. Electrostatic improvement by the new device geometry. So the goal is to consider the on-off ratio, where we try to keep our on current as high as possible, but also the off current as smaller as possible. And there's several strategies. The first one is we call the SOI. So we have a silicon on insulator. So basically, we put the insulator below the channel. So we try to reduce the current. Or another one is we call the FinFET. And the third one is we call the nanowire. So for the very recent advanced technology, like beyond 3 nanometer, actually you will start to talk, hear about the FinFET, you will start to hear about the nanosheet. And actually nanosheet is just another way of a nanowire, but the idea is very similar. So you can start to figure out that for the advanced node, actually the technology try to address issues, try to improve the electrostatic and try to increase the on-off ratio, try to avoid the off-leak current, try to reduce the leak current. So that's why the very latest technology is mainly focused on these issues. So the SOI is, the full name is silicon on insulator, and we have a tri-gate. It's actually we call the FinFET. We also have a surround gate, for example, that's we call the nanowire or gate all around. That's what we also call as a GAA. That's a gate all around technology. And nowadays, the main dominating technology for the advanced transistor is still related to the FinFET. So the idea of FinFET is that in the left-hand side, we have a planar. This is a planar transistor. So we have already talked about how the planar MOSFET operation. So we give the bias on the gate side, we give the bias on the drain side. You start to have an invert electron here, because this is positive bias. So your electron can be moved from the source to the drain. It becomes the current. But the problem is that we start to suffering the tunneling current because due to the very short channel length, and therefore we start to consider as a FinFET technology, where you have a gate has a 3-dimensional surround our channel region. So your channel is here. In here is only planar, so you can only control the channel from the top. But now you can control the channel not only from the top region, but also the side wall here and here. So that's we can efficiently to control the electrostatic, and in the end to make sure that we have very good on-off ratio. So this structure is mainly proposed by the Professor Tian-Li from the UC Berkeley. So this is the first result where his group published in the 1999 for the first FinFET demonstration. And the first FinFET demonstration is mainly on the P-FET. So this is a P-channel transistor. And then when we talk about the advanced logic device, actually one of the parameter we care the most is substrate hole sweep. So the substrate hole swing or substrate slope is a parameter to characterize this slope. And then this slope indicates that how fast of this transistor can turn on. So ideally, we hope this slope can be smaller as possible, because the smaller means that the slope is getting steeper. But if the slope is larger, that means the transistor, the turn on is actually the slower here. So this term is usually we call as a substrate hole slope. Or sometimes we just call as a SS. So you can see in this work, his group demonstrate the SS below the 60 millivolt per decade. Usually the bottleneck is around 70 millivolt per decade, because due to the some fundamental limitation come from the physics here. And in this work, he also demonstrated with an oxide size of a 2.7 nanometer. Of course, being the research and development, although the FinFET now is already in production with several new generation, even down to the 3 nanometer, but beyond the FinFET, there's still so many interesting device architecture that we are looking at now. So these are all the options beyond the FinFET. So you can see that in terms of the research and development, actually there's a very high demanding that people working in a different domain try to find the option that can possibly replace the FinFET here. And we will briefly talk one by one. By the way, each technology take like more than 10 to 20 years from the idea in then up to the production. So probably you won't see this technology right now, but probably you will see one of them in the next 10 years. So the first one we are actually working on is what we call the CMOS scaling. And ideally is we try to scaling the electrostatic and dry, and we would like to minimize the parasitic. So some of the terms you have already know that we have already explained. That's, for example, the SOI, the FinFET. We also have the 3-5 here. And this is a GAA, that's a gate all around. And then gate all around now is divided by the 2 different types. It's what we first one is a horizontal gate go around, and also another one is a vertical gate all around. And the bottom one, this is a carbon nanotube FET here. So we won't talk the device structure again for each one because it's pretty complicated. That's even take like another 10 hours is not enough to describe detail, but just for your information that for the very advanced research on this logic device, there are very lots of very novel approaches ongoing now. And another is we consider some new charge-based mechanism, switching mechanism, and that's beyond the semiconductor material, so beyond the typical material that we use. And the first one, for example, this one is what we call the T-FET here. That's what we call the tunneling FET. And also we have another, for example, this one is called the negative capacitance FET. And the negative capacitor FET is mainly enabled by the ferritic material. And we also have the 2D material FET here. So these are all the transistor based on the new type of operation or based on the new material. So that can be possibly become the new technology that can replace the FinFET. And also we have some more advanced concept. This is completely beyond charge based switching, and then this can be dramatically different from the CMOS logic. So you know nowadays the CMOS logic, the operation for CMOS is a main trend, is a main dominating technology in our semiconductor world. But if you try to implement this new concept, very new advanced transistor, that could be completely changed for the CMOS logic. So that means not only the device concept need to be revised, but also the circuit level, the circuit designer need to use a different way to design the circuit based on this new device. And some of the terms probably you are already heard very often recently, like the quantum computing or all spin logic, spin FET, that's based on some magnetic material. So these are all the possible as some advanced approach that can replace the FinFET. But of course, you know, this all take more than 10 years from the ideas and to the concept proof to prove that can have the better performance compared to the silicon FinFET. But also, before the production, there's still one main considerations related to the reliability. So all these technology we show here, to be honest, they all suffering huge reliability issues. And also lots of this technology haven't started to being conducted with the reliability testing yet. So we actually, the lots of the reliability physics inside this new technology is unknown. For example, the quantum computing, nobody has done the reliability in the quantum computing, although the quantum computing is a very fascinating technology, very promising. But in the end, once you reach a production, you still need to prove this quantum computing can be used for not only for the 1 week in the university, in the lab. It should be used for the 1 year, 2 years, 3 years in a different temperature region. So that's also need effort of the reliability understanding in all these new technology. So here, just try to give you the concept that when we consider logic device, what actually the performance we try to target here. Again, the IDVG curve, that's already good enough to allow us to understand so many things. So in here, we will still use IDVG as an example. But now, I will plot as a log drain current versus the gate voltage here. So in the conventional transistor here, we actually have the characteristic probably like in this way. So that's our conventional transistor. So we will define as this as our targeting output current. So that means we hope this transistor should deliver this kind of the current. And therefore, this transistor it needs to be biased at this voltage. So that's we should consider as a VDD here. But for the new generation, what we want to do is we want to make the transistor has a lower off current but in the meantime has a more steeper during the turn on here. And what would be the advantage if we have a transistor like in this curve? That means we can actually achieve the same output current, same targeting output current, but with a lower operation voltage. So that's the goal, to achieve the low power, right? So that's why we care a lot of the substantial swing. That's why in the previous slide I already mentioned why this sweep, this slope does matter for us. Why this slope is important? Because if this slope is steeper, in the end we can achieve the transistor produce the same current, but at the meantime with a lower operation voltage. That would be good for the low power consumption as well. And also, furthermore, if we can have this one much steeper like this, so that means we can even decrease our operating voltage. So the goal is to reduce our operation voltage. And nowadays, what we target is below 0.5 volt here. And to achieve, to efficiently decrease our operation voltage, what we have to consider is this slope. And we hope to design the transistor as the slope as steeper as possible. And this slope is how we call as a subthreshold slope. Of course, to achieve low power consumption, not only during the operation, we need to have enough output current, but with low bias. But at the meantime, during the non-operation timing, this offset D current also is important, because that will create lots of the additional power consumption in the non-operation state. So usually we will hope to have the device as a low I/O as well. So if we can make this transistor like this way, that would be the transistor that everyone wish to have. In the end, we can achieve the low power consumption. So that's a goal, how we, in the end, to fabricate the low power device that can save for our power consumption issues. So I hope right now you can understand why, if you look back for this first demonstration of this FinFET, I think right now you will get a little bit more sense why this curve is important. Because this curve demonstrates the good subthreshold swing. And also with the operation very low. This is below 0.5 volt. This operation is very low. And also, if we consider 0.5 volt here, actually we already have the enough output current, and on the other hand, the off current is kept in the relatively low. That's up to 10 to minus 12. So now, I believe you guys be able to analyze the key result from this figure. And analyze the key result from this figure is good because in the future, when you try to look at the literature, when you try to look at the device that you fabricate by yourself, you all know this is a key parameter, this is a key parameter, and this is a key parameter here. And furthermore, beyond the technology, actually we can consider what we call the more or more than more technology. And usually the one we try to fabricate to have the miniaturization, we try to do the scaling from the 19 nanometer down to the 7 nanometer, down to 3 nanometer and beyond. And this is the technology that we call the more. And the purpose for the more is to do the miniaturization. So that means we try to do the scaling, we try to make everything as smaller as possible. So that's in the domain we call the more. But on the other hand, there's another domain that we call the more than more. So the more than more is a technology that we don't have to deal with the scaling, but this technology is mainly consider the interacting with the people and environment. For example, some of the RF device, so it's not really need to go to the very smaller channel length, but what we care is about the high-speed communication, like the voltage, like the power device is also in the category of the more than more, or sensor, or the biochip here. So this slide just want to clarify that when people talk about some of the rumors happen in the past several years that once the Moore's law is dead, are we going to lose the job or not? Because the news reporters say that once the Moore's law is dead, that means we cannot make the transistor scaling anymore, and probably we will lose our job. But this is completely not true because there's still another domain. That's what we call the more than more. In the case of more than more, we don't care about the scaling. We care about the functionality. We care about this functionality where be able to interact with the people or environment or not. So here is some of the example that how the more and more technology can help us. So as you know, right now, nowadays, the data center server, because due to the AI, the booming of the AI, so nowadays the AI server or the data center server is the big market, and then this market and demanding continue to increase. So when we talk about the AI server, most of people, they will feel like, okay, it's important to have in the news, everyone is talking about the advanced package like CoWAS, like the 3D IC and so on. And actually not only the server need those advanced packaging, also this AI server also requires some of the advance in the power converting technology. So here is the idea. This is the power that actually being transported after the generating by the power planning and start to be delivered by this high V DC or high V transmission line here. So you can figure out that you can find out that actually the voltage applied here is voltage on top of this high voltage transmission line is extremely high. It's more than 10 kV. But actually the digital chip that we have to use, for example, our semiconductor, our notebook, our cell phone, it's actually we only need to have the 1 volt here. We only need to have a 1 volt DC. But actually the electricity, the electrical power generated by the power plant is starting from such a high AC. So we must do something to do the power transforming, power converting from the high power AC to a low power. And this is in reality how this semiconductor, especially related to the power semiconductor, that can be used in this domain. So first of all, we will have the distribution transformers, and then we have a UPS. So we start to transform to the 200 volt AC, and then we start to transform to the 400 volt DC, and then we still start to have the buck converter to down to the 408 volt, in the end to reach 1 volt DC. So this voltage transforming, and sometimes we call the voltage converting. That's because of the power converter. That's how this power converter is working. So try to convert the voltage and power from high voltage, high power to a low voltage, low power. But the problem is that each power converting, we actually will lose some energy. So you can see now we have a 98, 97, 98. Now we have 85 here. So actually, in the end, we lose a lot of the energy because there's no 100% ideal converting efficiency for each state. We always lose something, and then in the end, the lose is huge here. So that's why in the power electronics domain, especially related to the power converter, we can use some of the new material, for example, like in this case as a gallium nitride. And in the case with a new material like a gallium nitride, we can actually, this in the past, we need to have the two-stage converter, but now we can only use a one-stage converter. We can increase efficiency, and also that can save our energy loss. I think nowadays with using the gallium nitride, if this slide, if 5 years ago we talk about this, everyone is considered this still probably like the R&D technology, but this is not true at this moment because you can easily buy the gallium nitride based charger already in the market that everyone you can purchase. I think each one is less than 1,000 NTD. You can buy the gallium nitride charger here. So this is one example that how from the university R&D and then become the real product in the market. The gallium nitride is one of the example. Of course, when we talk about the power electronics, the converter is in one of the power electronic domain, but actually there are lots of the application. As long as we need to supply the power to our electronics, no matter for the consumer electronics, for the data center, for the automotive, or for the industry application, as long as we need to supply the voltage, supply the energy, we always need these power electronics here. I think nowadays most the hot topic now is, for example, this automotive. So automotive, especially if you consider for the electrical vehicle, you need to have this like the automotive driving by enabled by the power electronics, and nowadays many use silicon carbide as one of the new materials that are be able to enable for this application. So the key message is no matter for the logic low power or for the additional power converting, actually we always want to have the semiconductor that can give us a good solution to solve the power challenges. So the power challenge will keep driving the semiconductor innovation for the energy efficient electronics, because we are using more and more electronics now, but actually the energy consumed by these the electronics is actually getting huge and huge every day. So we need to have a new semiconductor technology to address these issues. So no matter in the low power device or some of the power electronics, so the goal is always the same. We try to reduce the energy waste here, because of we cannot supply that's enough energy for all these electronics. And then it will be interesting also to look at how the industry happening now. So this is a device option for the 2019 IDN. IDN is a flagship semiconductor conference happen every year. That's almost the latest research and development result that will be announced in this conference here. So this is from the slide from the TSMC. So you can see the FinFET, the first development for FinFET is from the 1999, but up to 2019, after 20 years, the FinFET still is a dominating technology here. So this is a good good example to let you know that actually what we are doing, I would not say every domain will be like this, but at least in the semiconductor domain, to be honest, what you learn from university is very valuable. It's very valuable in the industry for your future career, because what we are doing is pretty practical. We are not like the only doing for fun or for your pure research interest. Actually, what we are doing is, in the end, it's going to be the adoption in the industry. So FinFET is an example. FinFET that starting from 1999 so far, we're still working on the FinFET, try to do the more like the optimization, for example, fin width, fin profile. Of course, right now it's production, but we still need more and more high performance FinFET, so we still have the additional research and development for the advanced FinFET. And there's some still under them. This is development, and research. So this related nanosheet, nanowire, germanium, 2D material, and carbon nanotube. So you can see the knowledge you probably already heard or learned from this term actually is still very useful after you graduate, because you will still keep listening this term again and again, because these are all very promising technology. So this is 2019. So now you see the more advanced, more latest result. This is the slide from the IMEC from the last year. So you can see down to the 2024 for the 2 nanometer or beyond 2 nanometer, we still have some of the novelty, try to improve the transistor. And then the first one here, this is very similar to the FinFET, but now we have a channel all around here. This is channel all around here. So that's what we call the nanosheet. Nanosheet FET here. And also for more advanced, we have the fork sheet. And then we also have the CFET here. So these are the nanosheet based fab for the logic device roadmap in the future. And this term will start again to pop out as only you are in the semiconductor field. So right now everyone is talking about the CFAT. Yeah, we will also briefly explain the CFAT later. But the first development for CFAT is coming from 2015. And now in the last year, TSMC also demonstrated CFAT in IDM. So that means that everything is always starting from the research. So don't underestimate what you learn from the university, or don't underestimate what you gain the experience during the research, because after 10 years, 20 years, what you're doing is actually become the product that can be happen. So here is some more detail related to the different logic scaling roadmap here. So we have the left hand side, this is a triple gap FinFET. So as you see, this is development in university in the 1999, but so far we are still mainly use the FinFET. Of course, there's a difference in the pitch and fin height, but the basic structure of FinFET is very similar. And we also have this one is a GAA gate all around vertically stack. That's how we call the net. Also, we call we have the GAA vertically stack, and so this is a GAA vertically stack here. And sometimes we also call this as a nano sheet. FAT. And also this one is what we already mentioned, the fork sheet. And the last one is the CFAT. The idea of CFAT is just we try to stack the NMOS and PMOS together. So we have the NPMOS stack on top of each other. So this is what we call the CFAT. So this is a CFAT. As I mentioned, the first paper talk about CFAT is around 2015. But now in the last year, IDM, TSMC also demonstrate they really fabricate and demonstration the well function of the CFAT. So this slide is about the IMEC roadmap for the logic device. And then we can also look at this is the TSMC roadmap for the logic device up to 2025 here. So still, they are trying to optimize the FinFET. And beyond FinFET, they consider as a nano chip as well. So this is from the last year. And if you look at, just try to compare the different famous semiconductor institute or company, and then if you look at the Intel, it's a similar roadmap here. So the first FinFET is here. So this is FinFET in the Intel 22 nanometer, and then in this region, beyond the 28, they have the quality called the ribbon FET. Although it's just a different name, but actually the structure is still very similar to nanosheet. You can see this is just several stake of the sheet, nanosheet together. That's how they call the ribbon fat. But also they add additional, that's how they call the power via. So here we won't talk too much in detail. If you are interested in, there are so many material you can find in online. Try to look at their technology. Again, this is a roadmap from the Samsung. So still, the bottom one is a thin fab, and then the up one is what they call the gate, GAA. They just have a different name called the MBC fab, but it's actually just very similar to the GAA transistor as well. Okay, so this is also sometimes good to understand some of the ranking, the revenue ranking for the different company, and this is the latest result. This is from the first quarter in 2024, and we can know nowadays who is a main player, the company that has a huge, who is dominating in this business. And for sure, the first one is a TSMC. And the second one is a Samsung. And then the third one is a SMIC from the China here. And then the fourth one is UMC, GlobalFoundries. PSMC is also from Taiwan, and VIS is also from Taiwan. And this is a top 10 foundries by the revenue. But then if you look at the information, this is also the information in just a few weeks ago. That's a top semiconductor company revenues in the 2024, and nowadays the most dominating company now is for sure the NVIDIA, and the second one is Samsung, and so Broadcom, Intel, SK Hynix, Qualcomm, Micron, AMD, Infineon, MediaTek, Texas Instruments, and so on and so on. I think that once you are in this field, longer and longer, at least you will be very familiar with this company. Even you don't work for them, but you will know what they are doing and what's their product, because of all these companies, they have very great collaboration with Taiwan's semiconductor industry. Okay, so that's the introduction part. Okay, so we will start to further move with the time around the lab for the 10 to 15 minutes. I think we can start also a little bit continue for this part. That will be the second chapter, is related to the overview of the electronic device and their reliability. So still, before every time when we try to do the reliability, it's always good to understand the definition of reliability, because sometimes if you don't understand the definition, you probably will misunderstood how do we do the testing and what will be the expected outcome. So reliability is a probability of operating a product for given time period under the specific conditions. Without value. To be honest, just these three keywords, that's already pretty important for us once we start to analyze the reliability. The first one is a probability. So when we talk about probability, that means we definitely need to have the statistic tool. So we need to use some statistic tools to analyze this reliability. So we need to use some statistical tool. So that's why in this class we will introduce some of the basic statistic functions that allow us to analyze. Because once you start to make the product, you cannot possibly to test all of the product. Imagine that you produce like 1,000 wafers per day, or like the 10K wafer per month. How could possibly you can test all the 1,000 10K wafer every time? And then how can you possibly to test all the device on all this wafer? So actually what we are doing is we do the sampling. Sampling, that means that we only test a small amount of device, but we use some statistical tool to project the overall behavior. That's why we need to understand probability, we need to understand the statistical tools here. And the second part, important, is the time. That's we already mentioned last time, that the time-dependent characteristic is always crucial for the reliability. So we are not only care about the threshold voltage or gate current at one time, but actually we are care about how about after 1,000 hours, how about after 5 years. Does these characteristics still look good? That's actually the time-dependent behavior. And also the last part is a specific condition. So when we talk about reliability, it's also need to very clearly find that what's the condition we are talking about, because a different condition for sure give us a different reliability issues here. So for example, let's look at the JEDEC spec. So if you consider the JEDEC standard, we have already mentioned the JEDEC, and then one of the most important JEDEC testing is called HTRB. That's a high temperature, we use a gate bias here, high temperature gate bias. That's a high temperature gate bias. And the typical requirement for this HTGB in the JEDEC is, for example, 3,000 hours testing at one specific condition. For example, 150 Celsius degree, gate voltage unit applied at 10 volt. And then actually we have the test for sure, not only one device. Last time we already say it's this week, today we also say it's 3 different lots, and each lot we have 77 devices. So if you look at the requirement for JEDEC, is actually follow the definition for reliability very well. So time dependent is here. So when we talk about reliability, it's always talk about what does the time you mean for this reliability. So in this case, it's 3,000 hours. Yes, and then the next one is a probability, is here. So, as I say, it's not possible to test all of the wafer. It's not possible to test all of the device. So what we can do is only select the device, partial device. We do the partial testing, try to prove that would be this technology will be qualified. So the 3 laws and 77 device for each law is based on actually some of the analysis. It comes from the probability and statistically. And the last one is a condition. So this is our testing condition. So now you see, actually when we talk about reliability, we have to always consider what's the testing condition, what's the time factor, and what's actually how do you consider the probability here. So the JDEC standard is a very nice example just to completely follow the pure definition of the reliability. And therefore, in the next slide, we will start to talk about a little bit more about each term. The first one is the probability. Of course, everyone who already learned the probability from the high school, but probably we just didn't use that very often after you come to university. If you are in the engineering field, probably if you are in the more related to computer science or communication, probably you will use the probability a lot. But I believe most of you in this classroom is actually come from the physics, material science, or the electrical engineering, but it's more related to the hardware. And then in that case, actually, we don't use the probability a lot. So now it still need to do some review to remind everyone some basic knowledge related to probability. So probability is the sampling of a product for testing, and then the statistical analysis of a value test result, and then use the distribution function to describe population that fail. So now you can see the probability is basically like we only do the test on some limited device. So that's what we call the sampling. And then we use the statistic knowledge to analyze based on the distribution function. So in this class, we will talk about several distribution functions. Some of the distribution functions that you have already learned, like a normal distribution, like the Gaussian distribution, that's I believe you guys are very familiar with. But some of them, actually, you never heard about that. For example, the Weibull distribution, the log-normal distribution, that's actually the one we use very often in the reliability analysis. And so the part of this class, we will teach about how do we use this distribution function to analyze the result. And then the time dependency. So the time dependency of a reliability is implied by the definition, and therefore the time variables appears in all of the value distribution functions. So, like the bottom, the figure here. So, this is a figure from the some laptop, and then inside this laptop, you can find out some of the interconnection line, and inside interconnection line, you will find out there's a transistor here, and then one of the failure possibility for this transistor is because we have the defect. We have the defect here, so each defect will create a certain instability. So the ICs operate in the incredible harsh condition, turning on and turn off trillion times, and then during its lifetime. So this means that the operation, the reliability is always happen after the certain timing. And then the reliability is a time-dependent degradation. So it's basically, we have the time factor inside, and afterwards we have the time-dependent degradation. So the time can be varied from the quite large range. So this time-dependent degradation can start to sometimes happen 1 month or several years. And therefore, because the time dependent can be happen with such longer time range, so what we actually need to consider is a lifetime. So we need to make sure that the lifetime for our product can be safe in this time range. For example, if you try to make a product and you hope this product can survive for 3 years, then in the end, in the beginning, you have to have to estimate the lifetime that this product can operate in the certain amount of time, for example, 3 years, 5 years here. And then one more concept just want to mention, because also in the literature, we also very often to hear about the term. For sure, it's a time dependent. But on the upside of the time dependent is what we call the time zero. So sometimes people will also talk about the time zero phenomenon. But time zero phenomenon, it means that this is a phenomenon that we just characterize once, and we don't consider any time factor inside. But once we consider time factor, that we look at in the case with a time-dependent case. And here is one example of how the time-dependent degradation can happen. And this is in the case with the time-dependent dielectric breakdown. So as you see in the last slide, we already talked about there's one failure mechanism, what we call the time-dependent dielectric breakdown. So the name time-dependent is already obvious, shown in the title of this phenomenon here. So the time-dependent dielectric breakdown is mainly happen when we consider we have the gauge current versus the time. So this is So the x-axis is a time, and usually we prefer to plot this as a log to be easily observed phenomenon. Usually we will plot in the log scale here. And if we have to understand the time-dependent dielectric breakdown, and then first we have to understand the typical characteristic for the gate lead current. So we actually already mentioned, if you look at for the IG, VG curve here, the typical characteristic is like here. First, the lead current, as long as you give the gate bias, the lead current will start to gradually increase. And after a certain moment, you start to see the high current happen. And that's what we call the breakdown. But when we look at the time-dependent dielectric breakdown, actually we consider in the case we bias in this region. So if we constantly bias in this region, so what happened? So we bias at the VG, and of course we'll start to sense the leakage current here. And with a certain time happen, once we start to operate the VG with a certain amount of time up to here, there's a possibility this transistor will start to generate a defect in the dielectric. So this is a source, this is drain, this is our gate. And then the red square, that means the defect. But because right now we only have a generated small amount defect, so we won't, the gate current actually won't change a lot. But with the time passed by up to here, you can see the defect number is increased. So defect numbers are increased at this moment, but we still can have the relatively low gate current at this moment. But the less possibility reach to the case up to here, the defect is enough to form the leakage path, because right now the defect is side by side connecting with each other, and this can become as a leakage path. So once we have leakage path, that means your electron can start to go through this leakage path and become the very strong leakage current. So usually at this moment, you will start to see the high gate leakage current, because due to the enough defect, that formation of the leak current, and thus we still have the breakdown characteristic, just like here. So that's why we call this time-dependent breakdown, because in the beginning we sweep to high voltage, we found out that we'll break down at this voltage. But now if we operate in the lower bias, we will still see the breakdown. As long as the time is longer enough, we will still have the breakdown can be happen. This is because we start to have this leakage path. And the real name for this leakage path is what we call the percolation path. So that's a real name for the population part. And one thing we need to be careful is that during this operation, the defect will generate, and generate up to a certain moment here. But the problem is the defect generation is random. So we have the random defect generation. So therefore, that's why when we analyze the TDB, time-dependent breakdown, we also need to use a statistic tool. And actually the process of this random generate defect and up to a certain moment to form a leakage path is that we call the stochastic. So reliability is a stochastic process. So that's a stochastic process terminated by a threshold. So that means once reach a condition, then this stochastic process will be terminated here. So the stochastic it's a means having a random probability distribution. That can be analyzed statistically. So that's why, again, once we talk about reliability, it's always talk about the distribution function. It's always talk about we need to use some statistic tool because due to this statistically. And because of this phenomenon can be analyzed statistically, not be predict precisely. So similar, it's just like a quantum mechanism. It's the same. We can only predict the carrier behavior. We cannot predict precisely. We can only know about the probability. So similar that when we talk about reliability, it's always the same because the defect generation is random. So when we try to describe this behavior, we can only use a statistic tool to understand this random generation of the defect and use a certain distribution function. And we can statistically to understand the behavior, but we cannot predict the result precisely. Okay, so we will stop here and we will continue. So this just give a certain flavor for everyone that from this class, we will, part of this class will focus on the mathematical tool, which is mainly related to this distribution function.